All right. So, how was the homework assignment? Took like 30 minutes? No, 25 hours. Anybody have 25 hours beat? Did it at least work at the end of 25 hours? It worked after 25 hours. All right. So then it was worth the. Who spent at least 5 hours on it? At least 5 hours. At least who spent at least 10 hours? 2 days. Okay. Anybody spend less than 5 hours on it? It should have. Could be. Could be. Did you hear your buddy back there spent 25 hours on his homework? 25 hours. Man, that's dedication. Oh no, I mean I get it. I'm just impressed that he persevered. That's impressive. 25 hours. Well, you should get like a cake or something. All right, so let's see if I can solve it in less than 25 hours. Let's see what we can do. What was the homework first? It was that number one, right? So you take in like 125 plus 3 divided by 2 and do the math for it. All right. Okay. We've been using Adam in here, right? All right. Do you want to third button down? Thank you. You should probably be able to see that a lot better now, right? All right, let me get our project open. Open. Oh, wait, I think it was a reopen project, right? File, reopen. Row. Well, I guess it doesn't really matter. Just create a new file for this. I can't quite figure out how Adam's projects work, so we'll just. So this is CSC535 process expression, right? And I'll throw this in my download so it doesn't cramp up everything. .py. All right. So we are. I'm going to give us a starting point for this. So I'm going to give us a starting expression. And we'll set this expression up to be 123 plus 5 divided by 8 times 2. Something like that. Okay? That way we can keep working through this. Now I'm going to break this down into little steps. So I'm going to kind of approach this the way I would suggest you approach it when you're working on your homework. All right? Because these big numbers, working on it for 10, 12, 15, 25 hours, probably a lot of that time was you kind of meandering your way through confusion, right? You're kind of almost stuck out in the middle of a desert somewhere and like, well, what the heck do I do next? Because you don't want to make it any worse. So let's kind of take an approach here that I maybe would have expected you to do. All right, so the first step is we know we're going to have to walk through all this string because I'm going to need to piece these things out, right? I need to get that part. I need to get that part. I need to get that part. I need all those individual pieces in order to do something with the string. So we're going to start off by just going through my string, printing out each character. Make sure you're looping through the string. All right. So we'll create a little for loop. We'll say for I in range of 0 to the length of exp. All right, so that's going to take I on a voyage from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? Each time through, I want to go ahead and print the character I'm currently looking at in exp. So I'll print exp at position I. Make sense? So I'm going to be spinning through the string. This is just my for loop, making sure I'm walking through that string. one step at a time. All right, so we'll come out here, and I have that in my downloads. Python CSC535. Okay, so there's the contents of my string. So far, so good. We're not doing any of the real weird logic yet, but at least we're walking through the string. Go ahead. Yeah, so you could do this. The equivalent of this would be, I'll just write it in here. I probably would change the variable name to C because you're looking at characters. You're going to say for C in exp. Because in Python, technically, strings are collections. So this is saying each time we're going to go through exp and we want C to equal each of those characters. So then I could say something like that. And that'll print out all the characters as well. But what you do lose there is you do lose that variable I. So you don't know where in the string you are. Might not be a problem in this case, but do keep that in mind. They aren't 100% equivalent. The output here was the same in this particular example, but I no longer know whether I'm looking at character 4 or 5 or 6. I just know I have my current character as C. Does that make sense? All right, so I typically write it something like this, but the other one's called a for each loop. It's just as good. It's fine. In this particular problem, it actually wouldn't make a difference. We don't need the, in fact, using the for C in this particular problem might actually be a little cleaner. Might make it look like it makes more sense. I'm guessing that most people probably wrote the for loop like this, though. So let's solve it this way. All right. Your version would have a little bit less of stuff like this because you would just be able to say C and reference it. All right. So we know that one of the things we're going to have to do here is collect numbers, right? So what I'm going to do here is I'm going to forget about operators for a second. And I want to prove to myself that I can go through and I can collect 123 and spit that out to the screen. Then I want to prove I can collect the 5 and spit that out to the screen. Collect the 8, spit that out to the screen. Collect the 2, spit that out to the screen. Just kind of working on that little that maneuver of collecting a string, okay? So we talked about before that strings are immutable, right? You can't change them. So we're going to have to build up a string. So we're going to go ahead and I'm just going to create a string. I'm going to call it num1 for right now because that's going to be how we are going to use it here in a few minutes. And I'll just start that guy off as the empty string. I want to build onto him, right? So now as I'm walking through my string here, when I hit the 1, since that is a number, I'm going to keep it. I'm going to keep it. I'm going to keep it. But as soon as I hit that plus sign, I know I have finished gathering my first number, correct? So I need to be able to determine whether I'm looking at an operator. So what I'll do here is I'm going to create a list called ops. Actually, I can create a string called ops, right? So we have string find, don't we? So I'll create plus minus times divide and a string. You could have also done this in a list. All right, so those are all of our operators that we support, correct? So each time through, if I want to know whether I'm looking at an operator, I'm going to say if ops dot find my current expression at position I. So I'm looking for my current character in ops. If it's found, it'll give me something other than a -1, right? So we can say not equal to -1 if we want, or we can say greater than -1. Either one of those will give you a reasonable answer. So if what this guy right here says is if the character I'm currently looking at is an operator. The character I'm currently looking at is an operator. Let's go ahead and print out whatever's currently in num1. So I'm going to print num1, and then I'll say num1 gets reset to the empty string. Otherwise, if it's not an operator, it must be a number. So I should continue building up my number. So I'll say num1 is equal to num1 concatenated with exp at position I. Geez, is that going to let me do that? I think so. All right, so we'll do that. Now, what will end up happening is when our for loop is done here, we're going to have our very last number stuck inside of num1. So I'll go ahead and just do one more. Whoop. Print num1 outside of the for loop. Notice this guy is not indented inside the for loop, so he's not part of the for loop. That'll get my very last version of it. So if we kind of walk through this, what are we doing? Num1 starts off as the empty string. Is that guy an operator? No. Add it to num1. Is that guy an operator? No. Add it to num1. Is that guy an operator? No. Add it to num1. Is that guy an operator? Yes. Print out num1, which is 123, and then set num1 to the empty string. Then, is this guy an operator? No. Add it to num1. Is this guy an operator? Yes. What do? Print out the 5. 0 out num1. Is this guy an operator? No. Add it to num1. Is this guy an operator? Yes. What do? Print out, 0 it out. Finally, is this guy an operator? No. Then we're going to run out of string. So right now num1 holds a 2. And this for loop is going to end. So I'm going to be sitting out here and I need to print out my very final number, proving I've hit all the numbers. Does that make sense? So let me save that. So there's my 123, my 5, my 8, my 2. So those are my numbers, correct? All right, so now we kind of have that movement down of collecting a number. But now we kind of know we need to do some math along the way. Okay, so I'm going to go ahead and I'm going to write a little function. Let's put that function, we'll put it up here at the top. So we're going to, what's it? The syntax for a function. Proc. Functions. Show me a function. Def. This is my 4th language today. Today I've done Java. I've done, actually I did Python, so I did Python earlier, and then I did C. All right, so we're going to do def add nums, or no, def, let's call this guy DoMath. All right, and this guy's going to take an operator as a parameter. He's going to take a num1, and he's going to take a num2. All right, now depending on what kind of math we want to do, DoMath is going to do the appropriate math and return the result. All right, so forget about this other logic here for now. And also, keep in mind, if you're following what I'm doing here, I'm not solving the full problem yet. I'm solving little pieces of it, right? And I'm going to bring those together for my solution. So what I just did already is I collected a number. Now I know how to collect numbers. The next thing I know that I'm going to run into, and I'm already dealing with the logic for it, is I know I bump into operators. And sometimes when I bump into an operator, that's going to mean something. That might mean I need to do something, right? All right, so the thing that I would be doing when I bump into an operator sometimes is some math. I might be performing this operation on these two numbers. Make sense? So I'm just going to write a little function here that does that for me. So this guy's, depending on what op is, it's going to depend on what he's going to do to these. So I'll say if op is equal to the plus sign, then we'll return num1 plus num2. else if op is equal to the minus sign, return num1 minus num2. Elif op is equal to multiplication, return num1 times num2. Else, it must be division. Return num1 divided by num2. Now, you could have made the call in your version of this, whether you wanted to do integer division or if you wanted to do floating point division. But it doesn't matter. It's going to do correct math. You just have to decide what was important for you. So I'll just leave it like this. It'll give us exact math. All right, so that's our DoMath function. That function, I can throw 3 pieces of information. I can throw an operator and 2 numbers, and it will perform that mathematical operation and spit me the answer back, right? That's what that guy does. So any questions about this? So it's like I ran out to Home Depot, and I got this little tool that it looks like a gumball machine, right? And I drop 3 little things into the top of it, and a number comes out. And I'm going to use that number. So now I don't need to worry about the logic associated with that. I already wrote it. Okay, let's test that. Let's make sure this guy does what I want it to do. Okay, so here at the end, I'm going to go ahead, I'm going to print, what do I call it, DoMath? I'll print DoMath for the plus sign, and then 5 and 3. So that guy should give us an 8, right? Okay, so let's make sure. There's our 8. So that guy did what he was supposed to do. Let's test it for the other one. So let's do the minus. So it should give us a 2. There's our 2. Let's test it for the times. This should give us a 15. There's our 15. And then let's test it for the divide. This should give us 5 divided by 3 in floating point math. So it'll be a 6 something. That's weird. Gave it a 5, gave it a 3, 5. Oh, because these guys are, here, I just want to test something here real quick. Oh, so it defaulted to integer math if you gave it flat integers. So at that point, it didn't matter what we did. So it gives us a 1. It gave us the correct answer. Right? If I passed it floating point values, it would do floating point math. Otherwise, you could force it to do integer division with floating point numbers using the single slash, or rather using the double slash, slash. So if I use that, like we did last week, if I had passed the 5.0 and the 3.0 in there, this would also give me the 1. Because I did the double slash on that. 5.0 double slash 3 will give me a 1.0. It did the integer division version of that. All right, but we'll just leave it like this. We're going to be passing it whole numbers anyways. All right, so DoMath seems to do what we want it to do. So we have this nice little tool now that we can rely on to pass it an operator and 2 numbers, and it will do the math for us. That's handy. Okay, so now we have that tool. We'll just leave it to the side because we're going to need it here in a few minutes. So now we want to think about how are we going to work with this. Now, as I am walking through here and collecting my number, when I first start off, I'm going to be collecting my first number. Then when I hit an operator, that's the first operator I hit. I can't do math yet. Math requires 2 numbers, right? I can't do the addition until I also have the 5. So what I need to do now when I hit this operator is I need to store that somewhere. I need to remember my operators. And then I need to start building up another number, a second number. Now, when I hit this other operator, I'm going to say, do I need to do math yet? The answer is yes. Why? Because I've already seen 1 operator. And since I've already seen 1 operator, I must already have 2 numbers. That makes sense? I already have a num1, And presumably I've also collected a num2. And I've also collected the operator, the math I should do for those guys. So I need to go ahead and call do math on these guys. And then I need to store that answer somewhere. All right, what we're going to do is we're going to end up storing that inside of num1. So after the first number, we're just going to keep collecting num2 from that point forward. All right, so I'm going to have a little variable here called curop, and I'm going to start this guy off at the question mark. Now, did I give you some starting code last week for this? Yeah. Okay, so I gave you something that looks sort of like this. Okay, when I was looking through the solutions, I was wondering, like, it seemed like everybody used the starting point of a question mark. Maybe they got a hold of my code from previous years. I get paid either way, it doesn't matter. Okay, so I'm going to use that guy. So the question mark's just going to tell me there's nothing currently in there. Okay, so right here, this means I ran into an operator. I'm looking at an operator. Now I need to decide what am I going to do related to that operator. Well, if this is the first operator I've run into, that is, if curop is equal to the question mark, that is, if this guy is the first operator, go ahead and set curop equal to the operator we just read in. Okay? And then I'm going to need to switch which number I am currently collecting. So I'm going to give myself a, let's do a Boolean. So I'm going to give myself a Boolean variable called collect num1. I'm going to start that guy off as being true. All right. And I'm going to go ahead and give myself a num2 to collect as well, because I'm only actually going to collect num1 the very first time. Then I'm going to turn that off. So as long as collect num1 is equal to true, I'm going to be building up the number in num1. When it becomes false, I'm going to build up my number in num2. All right, you'll see how that's going to work here in a second. So when I find an operator, if it's the first operator we bumped into, store it. Else. Okay, now I'm going to go ahead and flip this. So if it's the first operator, we're going to store it. We're also going to go ahead and say collect num1 is equal to false. Since I just bumped into my first operator right here, I have finished collecting num1, so I don't want to collect that guy anymore. And you'll see how I'll use that logic here in a second. So now I've turned that off. All right, so that's what we'll do there. If curop is not currently equal to a question mark, that must mean I need to do some math. Correct? So the math I'm going to do is I'm going to go ahead and I'm going to get my answer. I'm going to store it in a separate variable just for a second. So I'm going to say answer is going to be equal to do math. I'm going to pass it my current operator. I'm going to pass it the integer version of what's in num1. I'm going to pass it the integer version of what's in num2. And I'll store that inside of answer. Make sense? All right. Then so that's going to give me a number. It's going to give me a solution for that operator. Then I'm going to go ahead and overwrite num1 with the string version of answer. Let's convert that guy back to a string. Okay, so that'll be the string version of answer. Put it back in num1. So I've replaced, the very first time I would have replaced num1, which was 123, with the string 128 in this example. All right. I also then need to say curop is going to equal exp at button I, or at bucket I rather. All right, so what does this logic in here say? It says, if I have not found an operator before, store the current operator, let's start collecting a different number. Otherwise, if this is not the first operator I've bumped into, that must mean I currently have values in num1 and in num2. So let's do my math with the operator I've previously collected. Then let's change num1 to the solution of that math. Then let's overwrite my current operator with the operator I'm looking at right now. Okay? Now, remember, in this else down here, that means we're collecting numbers. Now, the question is which number am I collecting? Am I collecting num1 or am I collecting num2? So we're going to say if collect num1, then we'll collect num1. Else, I'll just write it. Will collect in num2. Now this guy right here is actually saying if that guy is equal to true. That's just kind of redundant to write it this way. Because this is saying if true is equal to true, do this. If false is equal to true, do this. But if you like the way this looks better, it's a little bit less hidden. Kind of says exactly what we mean. If that value currently holds if this variable currently holds the value true, do this stuff. Okay, so we'll leave it like that. It's probably a little easier to read, even though it's slower because it's redundant on itself. True is always equal to true. False is never equal to true. All right, so we'll collect num1 as long as this guy is true. Otherwise, we'll collect num2. Now, as soon as we do our math here, when we did some math, we overwrote num1, we overwrote our cur-op, we also need to set num2 back equal to the empty string. Because from this point forward, we're always collecting our numbers inside of num2. Does that make sense? Okay, always collecting our numbers inside of num2. Now, yeah, this is fine. Okay, so questions about this so far. So this is the place where I might do math. This is the place where I'm collecting numbers in either num1 or in num2. Okay, and we're going to keep doing that for this duration of this for loop. Now, when this for loop finally ends, I might not be done, depending on the nature of stuff. In fact, I will never be done. I should still have some math to do potentially. I need to ask a question. So this is after that for loop. If cur-op is not equal to the question mark, because there is a possibility I could have read in just one number. I could have given it an input that looked just like that, in which case I would have never run into an operator. I would have collected num1, never run into an op, never collected num2, finished my loop. My answer is in num1, but I don't need to do any extra math. So I'm going to ask the question. This really says, do I need to do some math? If cur-op is not equal to the question mark, then what we're going to do is we're going to do the same thing we did here. Get our answer based on DoMath of the integer version of num1 and num2. Store that back in num1. Now, after that's done, regardless of whether I got into this if statement or not, I'm just going to print my final answer. Is what's in num1. That makes sense? All right, so now what I'm going to do is I'm going to take all this stuff here, all that logic we just wrote, and I'm going to put it inside of a function called process expression. And this guy will take an expression as a parameter, and then I'll paste all that logic inside of there. All right, so now I have a convenient way of calling that guy. So as long as I provide him with an expression, he does all the rest of the magic. So then down here in my main program, I'll say expression is that. Then I'll say process expression, EXP. Okay, so for this particular guy, this should be 123 plus 5, which is 128. 128 divided by 8 should give me 16, times 2 should give me 32. Oh, forgot to put a colon after my else. There's my 32. All right, so I'll go ahead and hide that because that's pretty straightforward. Questions about what we just wrote there in process expression? Anybody do it a substantially different way than that? Now, one thing I want you to, well, first of all, I obviously don't expect any of you to do it that quickly, right? I mean, I've done this a couple of times. But the issue is that what I really want you to get out of what we just did here is the process I went through to solve this problem. I didn't jump right in and say, how do I do this math? That's not the step I took. The step I took is I stared at that and said, here's the problem I'm presented with. I need to ultimately do the math that's stored inside that string. Okay. How do I accomplish that? Well, I'm not sure off the top of my head, but I know I'm going to need some individual pieces. So how do I go about collecting those individual pieces? So if you remember back a few minutes ago, the very first thing I did is I said, can I just collect the numbers and print them out? Proving that I can extract those little chunks from that string. That make sense? Okay. Now one thing is interesting here. I want to throw in some spaces. I want to know how int converts, if that'll convert, if a bunch of spaces followed by a 2 will accurately convert or not. That does still convert. Let's just assume for a second that that didn't work. What we just proved there is that int of that will give me the 2. Where that wasn't a guarantee. It's possible that tool would have said, look, this isn't a number. This is a bunch of gibberish followed by a number. But let's assume that we didn't know for sure that int would give us that. And I have my string that looks like this. What if I wanted to remove spaces from that guy? So I need to doctor my string up to give me a new string with all the spaces removed from the original one. That makes sense? So if I want to, so let's kind of solve this the same way we've just been thinking. So I'm going to say define remove spaces. This guy's going to take a string as a parameter, and he should return a new string that is like str, but with all spaces removed. Does it make sense what we're trying to do? Okay, so I'm going to pause. I want everybody to take, I'm not going to spend too much time, so some of you might not finish it in the amount of time, but I want you to at least approach the problem. We need to have practice. So let's take about 5 minutes and try to solve that problem. Okay, not a quiz. You're not going to hand it in. No pressure. Practice. Okay? So I'm going to pause this. So, how did it go? Well, did it go okay? How many of you think you solved it? How many of you think you almost solved it? who doesn't have a clue. That's okay. Not having a clue right now isn't the worst place to be when you're starting as a programmer. All right, so let's break this down. We've already decided strings are immutable, so we can't change them. Therefore, we're going to have to build a new one, right? So I'll go ahead and create a string maybe called answer. I'm going to start it off as being the empty string. And rather than remove spaces, what I want to do is I want to go through this string and I want to keep anything that's not a space and just tack it onto my answer. So this would actually be a good use for your for each loop with your for C in the string. So we could say for C in str, if C is not equal to a space, answer is equal to answer plus C. Oh, that's nice. Yeah. I think so. Yeah, it's kicking. Yeah, but thanks. Better safe than sorry. All right, so as long as what I'm looking at is not a space, let's go ahead and keep it. Once I'm done with that for loop, I'll go ahead and return answer. So that's remove spaces. Create another string to build our answer in. Loop through every character in our given string. You can loop however you want, either this way or the other way. If the character I'm currently looking at is not a space, this says not equal to. If whatever's in C is not equal to single quote space single quote, then we are going to keep it. So we'll say answer is going to equal whatever it currently equals concatenated with whatever's stored in C. And then we'll return our answer. Notice that return is not indented under the for loop. So this for loop will complete before we ever get to line 46 here. And then we'll return answer. So if we want to see that guy, I'll go ahead and say print remove spaces of exp. And that should turn this guy into the compressed version of it. So there's our spaces removed. Make sense? All right, so things like this, doing little problems like this, while they're challenging for you right now, is going to be a good way to practice and get better at this stuff. All right, so whenever you need to do a little tiny manipulation, all right, then, you know, getting that practice of just build. I mean, when you look at this after the fact, that's not a lot of code, right? It looks easy when you actually see the answer. But going from being presented with the problem and writing those specific lines of code, that's a little bit harder, right? All right, so that's only going to get better with some practice. Go ahead.
I think you talked about the split function last week.
That's fine. You still got to practice it again, right?
So I mean,
We talked about, I think, called a function called trim.
no,
Strip, yeah. But that only removes the spaces from the end. Let me show you what I mean. So if I say print, is it strip like that? Well, it's not showing up as a function, whatever. exp. If I say that, you'll see that it's going to look the same way as it looks right now.
I think you should write first the variable, then dot strip.
Oh, so it's exp.strip. Like that. It still doesn't look right to me. Let me make sure I'm using Python 3 here. Yep. So this is that stripped version. Because all strip does is remove spaces from the beginning and the end. Okay. In other languages, it's usually called trim. So it doesn't remove those spaces in the middle. Make sense? So it's not identical.
There is no any function to do that.
Most languages would not have that built in to remove spaces in the middle, but that's okay. Because we see that it's a pretty, put yourself in the shoes of somebody who's been programming for a little bit. You could imagine that's probably not very hard to write, correct? You see the answer. It took just a couple minutes to write while I was saying all this stuff out loud. So a programmer would be able to say, oh, I just need to quickly remove spaces. That might be something I need to do again in my program. So I'll go ahead and throw it inside of a function. That way I can call it multiple times. Whenever I need to remove all the spaces from something, I'll just toss it at this function and let him do it. So we don't really need it built into the language. In fact, that might be worse, because then all of a sudden you have this language with 4 zillion tools built into it, and it's hard to sort the usable ones versus the ones you might need once in a lifetime. That makes sense? So this type of thing you would just write yourself. That's another hint I would give you as well for learning how to program, getting better at programming, is when you run into a problem, like in this case, you decide, okay, I need to remove these spaces. Don't immediately run to Google and say, does this language have something built into it to do it? What I would encourage you to do now is, if you don't know it has something built in, then assume it does not. Solve it yourself. After you've solved it yourself, maybe then you can be a little curious and go look up and see if there happened to be a function built in that did what you just did. That makes sense? Eventually, once you don't need to practice these little things like this, then you can go look at the libraries and see, is there something already there, or do I just write it myself real quick? Then it might be worth spending a minute to look up the libraries. But something like this only took a minute to write. Once you have a competency in programming. So it might take less time just to write the stupid thing than to go look up and see if the thing's there. Does that make sense? So so that's our remove spaces. So that'll take anything out of there that we might have. All right, so with that in mind, one thing we might do, even though we saw a minute ago that we didn't actually have to do it, we could say expression is equal to remove spaces of expression. Then we'll call process expression on that now removed spaces version of it, even though we saw that we didn't actually have to remove the spaces. But we'll see that this guy still works. Row invalid with base 10. Interesting. It's actually very interesting. Let me do something here. Line 34. What did I break here? Invalid literal for int. So it didn't like me turning a 16.0 into an int. No, that's fine with that. Very interesting. Why can't I turn that into an int? So it's getting hung up right here. Isn't this the same input we had a few minutes ago? We didn't change anything, did we?
We're using Python 3 now.
Oh, that's the difference between Python, originally Python 2 and Python 3. So Python 2, our code still works. Python 3, it's complaining about us converting 16.0 into that. So we're going to have to typecast that guy to an int. Ooh. Num1 is equal to, let's go up to where we're setting it. So we're overwriting this. So that guy right there. And what do you want me to say here? String what? Oh, string of int of answer, like that. So it'll let me convert the 16.0 float into an int. Then I can convert that guy into a string. Yeah, that's weird that it won't let me convert the string representation of 16.0 into an int. So what this is doing is it's saying, in that example, answer is 16.0 as a floating point number. I then convert that floating point number into an integer. I then convert that integer into a string. Now it should work in Python 3. I really wonder why that is. Why you can't convert the string representation. I want to look that up real quick. Python 3 float in string to int. Maybe that's it. It won't convert a float into an int. I bet you can probably convert that into a float. If I say Python 3, run the interpreter, and I say, give me the the float version of 16.0, yeah, it can do that. But it won't give me the int version of 16.0 because it's saying, I'm not sure what you want me to do with the stuff that's after the decimal point. Traditionally, programming languages just say truncate that, cut it off after the decimal point, but this guy seems to want to give you a warning instead. Interesting. I didn't realize that that was a difference between the two. Okay. All right, so questions about that? Makes some reasonable sense what we've done here? I'll go ahead and copy all this code. I'll put it up on Slack. Oh, let me expand this guy so you get all of it. $535. All right, so there's that code up there. Oh yeah, that's the stuff I gave you last time. Okay, so now let's look at the book. And at this point, it looks like as a class, we have worked through sort of kind of the chapter on strings. We really haven't done much with the dictionaries yet, or classes, and then some of these other things are going to be the second 4 week stuff. Okay, so at this point, things that we should be familiar with are going to be the various types, so booleans, integers, strings, lists, dictionaries. The idea of branching, so that's conditionals, if statements, so asking a question, else ifs, those kind of things. Loops, so we've done a bunch of for loops now. Writing some functions. We've been working with strings quite a bit. and we've worked with lists and dictionaries some. All right, so what we want to do now is we want to start experimenting with, let's see, when I wrote, let me look at how I wrote insert and sort real quick. I took in a list that I actually have it return it, or I did as a pointer. Yeah, did as a pointer. Okay. So we want to look, we saw last time, let me just start with this. I'm going to delete all this stuff. If I create a list and I set this guy equal to 1, 2, 3, okay? And then I go ahead and I'm going to also create a function up here. So we'll call this guy change list. And this guy will take a list as a parameter. And what I'll do is I'll say list at bucket 1 is equal to a -5. Just for no good reason, just I'm changing that list. All right, so I'll come down here, I'm going to print out list. Then I'll call change list on my list. And then I'll print out list again. Okay, so my list is 1, 2, 3. I'll print it out. It should print out 1, 2, 3. Then I'm passing it to change list up here. So my list 1, 2, 3 is coming in here. I'm changing bucket 1 of that to a -5. Then back out here, this guy's going to print out 1, -5, 3. And that's going to happen because when we pass this list here, it's getting passed by address into this function. So when this guy's making a change to that list, he's changing its actual location up in memory. That make sense? All right, so let's go ahead and run this. We expect to see 1, 2, 3 here. We expect to see 1, -5, 3 here. Even though change list didn't actually return a value. It just modified our list up in memory. So there's our 1, 2, 3, and there's our 1, -5, 3. Make sense? Okay. So now, what about dictionaries? Let's see how dictionaries are passed. So I'll go ahead and I'm going to create a, let's see, we'll just create a dictionary, D. This guy is going to be equal to, let's say, A:1, B:2, C:3, like that. All right, so that's going to be our dictionary. I'll go ahead and let's just comment these guys out. We'll go ahead and print out D. Let me just see real quick how dictionaries look when we print them out. All right, so that's printing out the contents of that dictionary in a easily readable thing. I'm going to create another function here, def change dict. And this guy will take a D as a parameter, and we'll go ahead and say D at position B gets a -5. So we'll call change dict. We will pass it our dictionary, then we'll print out our dictionary again. All right, so we want to determine whether dictionaries are passed by address or passed by value. It's going to be passed by address if the output shows, well, the first time we already saw what it shows, A1, B2, C3. If after we call change dict, it prints out A1, B -5, C3, then we know it's being passed by address. If instead it prints out A1, B2, C3, it's being passed by value. And I mentioned before that historically, dictionaries kind of sound like structs. We've talked about structs from older languages like C, C++. Structs are passed by value. So we want to see how dictionaries are actually passed in Python. They are passed by address. Make sense? So if we pass a dictionary to something and it changes, it permanently changes. Okay. So now what we want to do is we want to play around with dictionaries a little bit and get, let me actually just do some quick math here on time. Yeah, let's keep going for a little bit longer, then we'll take a break, then we'll just do one final hour. Is that cool? We're all comfortable? Okay. So what I want to do is I want to create a kind of a quick way to create some dictionaries. So what we're going to do is I'll create a little function, def, and we're going to call this guy, let's see, we're going to have maybe soccer players, right? So we're going to call this guy make player, and a player is going to have a name, and a player is going to have a jersey number, something like that. And then what we're going to go ahead and do is we're going to return a dictionary. So we're going to create a empty dictionary here. Actually, we don't even have to create an empty dictionary. We can create a dictionary that has a name, whose value will be name, and who has a jersey number that has a value of jersey number. And then I'll go ahead and return that dictionary. Okay, so now I've given myself a little convenience function. I can call make player, I can pass it a name and a jersey number, and it will go ahead and build for me a dictionary containing those two pieces of information and return it for me. Okay? So now I can do something like, let's do it, well, here, we'll just make a one player real quick. So we'll call P1 is equal to make player, and we'll call this guy player 1, and he's going to be jersey number 1. Okay? Then we'll go ahead and print out P1, and this should give us the dictionary for that player. So we're storing some information. This is kind of a variable capable of holding more than one piece of information about a player. All right, now what if I want to hold 100 different players? Something like that. I would probably create a loop, right? So what I'm going to do is I'm going to create a list to hold my players. Maybe not do 100, let's do 20. We'll be able to read that a little bit. It's more like a normal team, 20 players on a team. Go with that. So we're going to have players is going to be equal to the empty list. So what I'm going to do is I'm going to create a list containing a bunch of players, where a player is a dictionary. Okay? So I'm going to have an empty list here. I'm going to create a for loop. So for I in range of 1 to 21, so that'll go to 1 to 20. Then we're going to go ahead and say players.append. And actually, we could just players append, put something in there, right? Yeah. Then we'll say make player, and we're going to pass it the string player space concatenated with I, and then we'll give them jersey number I. And then we'll go ahead and print players. All right, so this loop goes through all the numbers between 1 and 20. Each time through, we're going to append onto our list players whatever's returned by our function makePlayer. What does makePlayer do? It takes in a player's name, so we're going to be passing in like player 1, player 2, player 3, player 4, and then a jersey number. It constructs a dictionary of that information and returns it for us. We're going to then append that dictionary to this list of players and print it out. Need to give it the string version of that integer. We can't just concatenate them directly. All right, so there's our players. Player 1, player 2, all that stuff. Make sense? Okay. So now what we're going to do is let's add a little bit of randomness to this. So we've had a random number generator, right? So that's just called rand. Print. Python random. I think I had it in our insertion and sort, right? We imported random, random.randint. Okay. So I'll go up here. I'm going to go ahead and import random into this. And then rather than give us a, use the player number as the jersey, we're going to go ahead and say random.randint. And we'll do 1 to, we'll do 1 to 100. All right, so now we have players that have random jersey numbers. We might have repeats, potentially, but they have random jersey numbers. That makes sense? All right, so now what we have is we have a collection of dictionaries where each dictionary represents a player. All right, so now, what if we wanted to sort our players on their jersey number so that the smallest jersey numbers come up first, the larger jersey numbers come up second? So before we sorted some integers, right? Just flat integers, and we put them in ascending order. Well, now my types that I'm trying to sort aren't so simple. I have these dictionaries that contain some additional information. So now what we're going to do is we're going to go ahead and rewrite that insertion sort for our players, specifically to sort them based on jersey number. Make sense? So we're going to use the same algorithm we wrote before, but instead of comparing the value at these different places, we're going to compare the jersey number that lives within the value at each of these places. Ay, ay, ay. There we go. All right, so now let's create a def sort players, and this guy will take in our list of players. Now, keep in mind that that variable there does not have to match this guy. I could call this guy elephant if I want, and then pass players into there, and then inside here I have to refer to it as elephant. So maybe we can say, give me a list of players as an input here. So whatever list of players you have, I am then going to sort that list of players. Okay? So remember, we kind of go from bucket 1 all the way to the end and then move stuff towards the beginning. That's how insertion sort worked. So we'll create our standard for loop. So for I in range of 1 to length of list of players. And then we're going to need a variable. So we're going to say follower is equal to I, because that's going to be the I don't like that it replaces that stuff. So follower is going to be the guy that keeps bubbling up to the top as we are swapping players. Okay? So we're going to ask the question. We're going to say, while follower is greater than 0, so as long as that guy's not at the beginning of the list, as long as we have somebody before us, and now I want to get the value that lives before follower. So if we say list of players at bucket follower, that's going to give us a dictionary. I want to then ask that dictionary for his jersey number. That makes sense? So I'm going to say if follower is greater than 0 and list of players at position follower's jersey number, is less than list of players at position follower minus 1's jersey number. If both of those things are true, if I'm not at the beginning of the list and the current guy's jersey number is less than the previous guy's jersey number. So I'm extracting one additional piece of information. My list is called list of players. List at position follower will give me one of those players, but that's a dictionary. Then I need to ask that dictionary for his jersey number. Okay? So if I'm not at the beginning and the guy I'm currently looking at has a smaller jersey number than the previous guy, I need to swap. Put my colon down here. So I'll say temp is equal to list of players at bucket follower. Then I'll say list of players at bucket follower is equal to list of players at bucket follower minus 1. Then I'll say list of players at bucket follower minus 1 is equal to temp. So I'll swap those two guys. That makes sense? Same logic we did before we wrote insertion sort. We just happen to be swapping dictionaries instead of numbers. All right? So temporarily store the player that lives at position follower, then replace that position with the guy before him, then replace the guy before him with the value temporarily held. So we kind of put this guy on hold, overwrite him, and then overwrite this guy with the guy we stored. Okay? And we're going to keep doing that while loop as long as we either haven't gotten to the beginning of the list or we should keep swapping. Otherwise, when this while loop ends, we spin back up, we move to the next value of I, follower resets to the new value of I, and we do that positioning again. All right, so that's sort players. So now I can print out players. I can then call sort players, and then I can print players again. And actually, we won't even print it the first time. I think it'll be pretty obvious that randomly we're not going to get jerseys that are in ascending order. So if it looks like it's in ascending order now, we should be in pretty good shape. So jersey number 70. Whoa. That did not change it. That's because I didn't actually finish calling. Why didn't I even give me an error? Maybe I didn't even save it. I might not have saved it. I need to call sort players and pass it my players. I didn't even call my function. Okay, there we go. Yeah, there's 6, then 26 and 56. Is it still? That's 32. That doesn't look right to me. That's very strange. Let's take a look. I'm calling sort players. I'm passing it my players. If we print players beforehand, which I didn't think we needed to do, but let's do it. Let me just clear this real quick. All right, so things are moving around. My algorithm here must be wrong. Sort players takes in our list of players. I go from bucket 1 up to, but not including, the last element in list of players. I start follower off at I, as long as follower is greater than 0 and the guy at position follower is less than, are we storing numbers in there? We're storing numbers in there. The guy at position follower's jersey number is less than the guy at position follower -1's jersey number. As long as that's true, do the swap. So we'll temporarily store position follower. Then we'll overwrite follower with the previous guy. Then we'll overwrite the previous guy with temp. That looks correct to me. Let me just try something here real quick. This should not make a difference. Yeah, it didn't make a difference. Oh, I know exactly why. All right. This is actually this is actually a really good example. This code works fine. Anybody know from the reading why this is not printing it out the way you want it to print it out? It's a very special thing with dictionaries. See, dictionaries, they do not guarantee us what order they store the stuff internally. So we're swapping them around, no problem. Okay? But that isn't necessarily changing the internal representation. In fact, it actually is changing it, but not changing it the way we wanted it to. So when you create a dictionary, it doesn't matter what order you put stuff in there. It will show the stuff in whatever order it thinks. In fact, it'll be very interesting. Let me not sort here and just print it once. I want to know if it happens to give us the players in the right order. It's player 1, player 2. Yeah, it happens to store those guys in the right order. So now when we start changing stuff around though, so when we initially built it, it stored it in a reasonable way. But now look, we have player 1, we have player 3, then we have player 2, then player 5. So it's clearly moved stuff around in our dictionary. But dictionaries do not guarantee the order that they are storing stuff internally. So there isn't really a such thing as sorting a dictionary. Although sorting a list, actually, hold on, sorting a list should have worked. Yeah, so we're still not, we're not correct yet here. Sorting a list should definitely be a thing, and that's what we have here, is we have a list. We have a list of dictionaries. So this should work. Oh, I did, didn't I? Yeah, because remember, I do it in that really deep voice. It's like, the follower follows. So here, the issue is that after we do this swap right here, what I'm doing is I'm just staying in place and swapping again. After I've done the swap, the follower has to follow back up the list. So after I've looked up and I said, okay, I need to swap myself with the guy before me, then I need to jump there and say, okay, I'm going to check now him before me. So the follower is going to move towards the beginning of the list. So we weren't decrementing follower here. My mistake. So now this guy should give us a sorted list, because lists do guarantee order. Jersey number 10, 19, 19, 24, 36, 38, 43. Looks like they're sorted now. All right, so now we have, in case we care, a list of sorted players by their jersey number. So we used the exact same algorithm as we wrote before, except this time we dug in one level deeper and asked about the specific jersey number in that value. And that's actually helpful for us because now we can look at this and say, you know, I can store chunks of information inside of dictionaries like this. So it's kind of like a super variable. Instead of just holding a single value like a number, I can now hold a first name and a last name and a jersey number and a telephone number, and I can hold patient record stuff, things like that, right? Okay, so let me, I want to just introduce a concept to you right now. We're not going to use it yet today, but I'm going to introduce it to you. It'll take about 5 minutes or so, and then we'll take a break. So, how many of you have heard of something called recursion? When I say recursion, what does that mean? Sort of, kind of looping? All right. So, recursion, or a recursively specified function, is a function that is implemented in terms of itself. Okay? We could also say is a function that calls itself from within itself. Both of those kind of say the same thing. And usually when you first teach recursion, the first way you show it is you show some math problem that's recursive. So for instance, if I say 4 factorial, 4 factorial, that's 4 times 3 times 2 times 1, right? That's what 4 factorial is. So 4 times 3 is 12, 12 times 2 is 24, times 1 is 1, so this is a 24. All right? Now we can certainly write that iteratively. We can come down here and we can write, I'll not print here. I'll go ahead and I'm going to define fact iter, because that'll be the iterative version of factorial. And this guy will take in a number, and we will count. We'll say for I in range. Now, if we want to count backwards, we can. So we could say I in range from num down to 1, step by -1. Okay, because we don't actually have to go all the way to 1. We can stop at 2 because anything times 1 is itself. But if we want to go all the way to 1 and just be explicit, we'll say starting at num goes all the way down to 0, not including 0. So it goes down to 1, steps by -1. And then we're going to need to build up our answer. So our answer will start off as 1. And we'll say answer is equal to answer times I. And then I'll return answer. So this is the iterative version of factorial. I pass it a number, for instance, 4. I start my answer off at 1. I start I off at 4 and count down to 1. Answer is equal to whatever it currently is, which is 1, times 4. So now it's 4. 4 becomes 3. Answer is equal to 4 times 3, which is 12. 3 becomes 2. 12 times 2 is 24. 2 becomes 1. 24 times 1 is 24. Finally, the answer is 24. Return answer. So we can say print fact iter of 4. And that gives us our 24. All right, so we are iteratively going through that guy, not recursively. Now, if we're looking at recursion, though, 4 factorial is equal to 4 times 3 factorial. 3 factorial is equal to 3 times 2 factorial. 2 factorial is equal to 2 times 1 factorial. And 1 factorial is equal to 1. See how that works? So now we're saying that factorial is implemented in terms of itself. 4 factorial is equal to 4 times whatever 3 factorial returns. 3 factorial is equal to 3 times whatever 2 factorial returns. 2 factorial is equal to 2 times whatever 1 factorial returns. And 1 factorial, that's where it finally ends, returns a 1. We stop calling the recursive function. So if we want to write this guy recursively, say def fact rec. All right, so we'll ask the question if num is equal to 1, return 1, else return num times fact rec of num minus 1. That's the recursive version of factorial. So if num was 4, is 4 equal to 1? Nope. We drop down to the else, return 4 times whatever the factorial of 3 is. So now we put this on hold, come back up here, num is now 3. Is 3 equal to 1? Nope. We're going to return 3 times whatever the factorial of 2 is. Put that on hold. Come back up here, now we're 2. Is 2 equal to 1? Nope. So we're going to return 2 times whatever the factorial of 1 is. Put that on hold. Come back up, now we're at 1. Is num equal to 1? It is. So return a 1, which finally gives us then our answer for the factorial of 2, which finally then gives us our answer for the factorial of 3, which finally gives us our answer for the factorial of 4, which then returns the final solution. So if I print out fact rec of 4, we should get the same. Oh, forgot my colon on my else. We should get the same answer. So then my question would be, which is better? The recursive version or the iterative version? A lot of languages, you wouldn't have to indent so much like this, so you could actually write the recursive version pretty shortly. You can do it almost in one line. So a lot of times recursive solutions look shorter, but that isn't necessarily always better. What do you think is the downside of something being implemented recursively? What's bad about that? As I was walking through this, wasn't I kind of saying we have to wait for stuff? So before I could return the answer for 4 factorial, I had to wait for the answer to 3 factorial to finish. And 3 factorial couldn't finish until 2 factorial finished. So he had to wait on 2 factorial. 2 factorial couldn't finish until 1 factorial had finished. So he had to wait on 1 factorial. So what you end up having to do is we're pausing a whole bunch of copies of this function. And that takes up a lot of memory. Okay, so we would call recursion recursive tends to be elegant solutions. So a lot of times the solutions kind of look cool, almost mysteriously cool. Sometimes you can see solutions in recursion that are really hard to understand because you really have to think about how does this actually unravel to give you an answer. And from that perspective, a lot of times recursion might not be the best because, recursion makes sense when it makes sense. But to just do something recursively, just to do it recursively, might introduce code that's difficult for somebody else to read. All right. So recursive gives elegant solutions, typically give short solutions in terms of the number of lines of code, but this is memory inefficient. So it uses a lot of memory for recursion. All right. Iterative, we might say less elegant solutions, potentially longer solutions, but these guys are memory efficient, relatively speaking. Because an iterative solution is not going to have to put the whole function on hold and then call itself again to work on the next part of the problem. So now you have 20 versions of the function sitting in memory instead of just one version of the function. Does that make sense? So the answer is it depends. One's not necessarily better or worse than the other one. They both exist. Recursive functions are, I would say that, I'm just pulling a number out of the sky here, probably something like 3% of functions would be written recursively. So a very small number, but it's not a never thing. So every now and then you'll run into something where you write a function recursively. Now, the one thing I'll tell you, and so this will give you some relief. First of all, most of you probably had a little trouble following the recursion thing here. And this is the most simple example of recursion. I won't test you over recursion. I won't give you code and tell you that it's recursive and say, what does this do? I won't ask you to write code that's recursive. I just wanted to introduce it as a topic. In the next class, we might do some more of this, but our undergrad students in computer science, when they've had programming for years, right? So they've had 3.5 years of programming, let's say, or let's say 2.5 years of programming. They still suck at recursion. And part of that is because you don't run into it very often. So they haven't gotten a lot of practice, those reps. They don't have those reps in for working with recursion. But when I teach the 470 class, which is our programming language theory class, I use a language in there called Scheme. And what's cool about Scheme is it does not have loops. So you have to implement everything recursively. So by the time they get out of that class, they're pretty good at recursion. And then the funny aftermath of that is they have solving problems iteratively after that because they see recursion in everything. So I just wanted to introduce the topic to you just in case you end up not taking the next class. I do encourage you to take the next class. I know that the content feels difficult, right? Content feels difficult, but it will benefit you in your job taking the next class. If you just absolutely come out of here and you hate programming, don't take it. That means you're going to avoid programming like the plague your entire career. But if you kind of like programming, you just think you suck at it, definitely take it. You're going to end up having a better grade than you think you deserve in the class because I have to curve the heck out of things. What's this? It is elective. Yeah, this class is required. The other class is an elective. But you got to take 2 electives, right? So you got to get to pick your poison. If you're interested in programming, take the programming elective. If you're not, don't.
I think this one.
This is enough? Really? So you don't want to do any programming in your job?
I don't have. In my job, no, there's not any programming.
Well, these ladies already signed up for the next class.
Really?
I doubt it. Out of curiosity, who in here is planning on taking the 537 class?
What is the content of that?
The who?
What's the content? What are you going to do?
We will be doing Java and Android programming. So we'll be writing Android applications in there.
Do you have the classes next session?
537 is offered, not the second 8 weeks, it's offered, I think, next fall. Either session A or session B. I don't know which of the two. One of those 2 sessions in the fall. But you'll learn how to write Android applications in there. So. And it's, of course, 10 times harder than this class. So promise, I'm going to see you there, right?
Wait, for real?
What's up?
For real?
Well, I mean, what's harder? I mean, in some ways, I would say it's harder. In other ways, I think it's more fun. Because this is kind of boring stuff, right? When you're constantly looking at your output in like a text-based screen, it's like boring. But we're having to use kind of let's call it a weaker language. Where when we're writing Android applications, you're going to have like a simulator showing up that looks like a phone. But the code you're writing is the same stuff. You'll be writing if statements, you'll be declaring variables. You're just responding to button clicks and stuff. In fact, I might even say that the stuff you do some of the stuff you do in there will be easier, but you'll be solving harder problems. But you'll be solving them in terms of Android, which will make life a little easier. So it's probably similar difficulty. You'll be a little bit better when you're in that class, so I would say the class is probably going to feel about the same level of difficulty as this class. Something like that.
So it's harder.
I don't know. Typically, the grades in that class are better grades. You know, because in this class, you know, you have also, everybody's forced to take this class, right? You know, you're a captive audience. So you get a whole bunch of B range grades in here, and then you get the couple of people that get up into the A range. So probably, you know, if you are in the B range in here, but you like programming, I encourage you to take that class. If you're in the A range in here when we're done, chances are you either like programming, or whether you like it or not, you're better at programming than you think. I would definitely take that class because I think that's going to, you kind of have a predisposition for programming stuff, and you'll probably end up doing some of that in industry. And then that class maybe makes sense. You know, but if you scoot by with a B- in here and like, I'm not going to lose sleep if I never see programming again, don't take it. Pick one of the other electives that makes more sense for what you plan on doing in your daily life. Okay? But it's a class that a lot of people have taken advantage of. A lot of the graduates who come out of here who've gone through the 537 class go and get jobs as software developers. So what's changed here is we have a master's in computer science program now, but historically we didn't. We had a master's in just IT. So we had several students who kind of came into this program. They came into the IT program because we didn't have a CS program, right? And by the time we offered the CS program, they were halfway done with their IT one, so it just didn't make sense to start over. So the 537 makes plenty of sense to them because they want to go out and do computer science industry work, but their degree is in IT, so they might as well get as much programming background as they can. And probably the easiest way to get hired in programming today is through iOS or Android development. Mobile application development is a big thing, and virtual reality is kind of the second thing. We actually also have a crossover course in the Masters of Computer Science. We have a programming class there where we do virtual reality programming that we have had students from the MSIT program go over and take that to count as their electives to learn VR programming. It's a 6 credit hour class and it'll count as 2 electives. But you have to get special permission for that. That's really those people that probably would have done the Masters in CS had they not already started the IT. So that's going to be less of an issue now since we've had the CS for several years now, but I'm kind of talking historically.
Is that VR class a whole semester or?
Whole semester, yeah. So it's a similar format to this, where it's one night a week for 4 hours, but it's all 16 weeks, but it's 6 credits. So it's you get a double elective out of it. And I'm thinking, when's the next time that actually won't be offered again until see, that was just offered last semester, so it won't be offered again for a year and a half. Yeah, so you get burned there. But we could always do an independent study if Dr. Locklear approves it. Okay, so questions about the recursion stuff? All right, let's take about a 15-minute break. Then we'll come back, and I'm going to introduce some other new stuff, and I'll give you your impossible homework for this week. And then we will cry ourselves to sleep.